Hey guys, how we doing? We're starting chapter 10, and Mr. Bidello went to the bathroom or something. So we're starting into chapter 10, and chapter 10 is pretty basic shape, but we haven't talked really about it all year for whatever reasons. And so we're talking about circles here. And so we just need to look at some vocabulary terms like we typically do in the first section of every chapter. And I'm sure most of these are terms that you've heard over and over again, but some of them might be new. Actually, a few of them probably are new. And so you just need to make sure that you're prepared to write down some definitions here and so on as we go through these notes here. But this is section 1 of chapter 10. And so we have a diagram here with a circle. And basically the definition of a circle is the set of all points in a plane, and that's very specific, the set of all points in a plane that are equidistant from a given point. And we call that given point the center. And so if you think about that, if you draw the center and then you make every point that you can that's say 5 inches away from that point, it ends up creating a circle, as long as you stay in a plane, a piece of paper, whiteboard, whatever. If you didn't have that in a plane in the definition, then it would end up creating a sphere or a ball, because then you could make ones that are 5 inches in front of it, 5 inches, to the side of it, and behind it, and so on, and it would create a sphere. And so it'd be a three-dimensional shape. And so a circle is the set of all points in a plane that are equidistant from a given point called the center. And then we have specific pieces of that. So the center, of course, is the middle of the circle, very center of the circle that the circle radius is drawn from and so on, measured from. The radius really is the main measurement of a circle. That's how we determine how big a circle is. And so the radius is a segment, a line segment that goes from the center of the circle out to the edge of the circle itself, to the points that are on the circle. And so so that radius is always a measurement. And the radius can be drawn anywhere in the circle, and it's the same measurement no matter where you draw it in the circle. Radius is always congruent to another radius in the same circle. Okay. Then of course we have a chord, and a chord in this diagram, and that may be a new term for you. A chord is a segment a line segment whose endpoints are on the circle. And so if you notice that green line there, the endpoints of that segment, one is on one side of the circle, one's on the other. So you could draw a chord, lots of different lengths of chords. You could have really short chords, you could have long chords, and as long as the endpoints are on the circle itself, that's a chord of a circle. Okay. A very specific chord, or one specific chord, is a chord that crosses through the center of the circle. And that kind of chord is called a diameter. Okay, and so a diameter is defined to be a chord, and as long as that chord passes through the center, then it is a diameter. And of course, we have a special relationship for a diameter. The question here is there a radius in a diameter? Yes, there is. We all know, I think, that a diameter is made up of 2 radii. Radii is the plural of radius. We don't say radius is. So a radii is plural of radius, and if there is 2 radii put together across a circle, that creates a diameter. So yes, there is a radius and a diameter. There's 2 of them, and the relationship would be 2 times the radius gives you the diameter. All right? So those are some of the basic definitions for basic vocabulary that we need throughout the rest of this chapter. So you definitely need to know what those terms mean. Okay? Here are a few more terms, more circle definitions here. And so we have some other lines that we're looking at, specifically a secant line, it is called. A secant is a line that intersects a circle in 2 points, exactly 2 points. Okay? And so that green line in this diagram is a secant line. Okay? Well, another line in this diagram is a tangent line. And a tangent line is a line that intersects a circle in exactly 1 point. You've got to think about that a little bit, how that could happen. But you see in the diagram there that a line is just barely touching the edge of the circle, and that's called a tangent line. It has nothing to do with tangent when we talked about trig, sine, cosine, tangent, nothing to do with that. This is a completely different kind of tangent. Okay? And so a tangent line is a line that hits a circle in exactly 1 point. So it just barely skims by the circle and just touches it. Okay? And so line AB here is a tangent line in this diagram. Okay? And that point that it hits on the circle, point B in this particular case, is called a point of tangency. A point of tangency, so that point where it hits the circle is called the point of tangency. Okay, notice the spelling of that. It doesn't have a T in it at the end. It's just tangency. All right. We need to be able to answer this question here. Okay, is there a chord? So we got to remember what a chord is from the last slide. Is there a chord in a secant? And what's the difference between a chord and a secant? Because we said a chord hits a circle in two places too. And so we need to understand the difference. So a secant is a secant line. A secant is a line that passes all the way through a circle, hits it in two places. Okay? A chord is a line segment whose endpoints are on the circle. So basically a chord is part of a secant. A chord is the line segment that starts at the circle and ends at the circle. The secant goes all the way through the circle. So something I'd like you to think about here, we can put up those answers to those questions. Something I'd like you to think about here is when you draw a circle on a piece of paper and draw a line on that piece of paper, one of three things is going to happen. Either that line and that circle will never hit each other. You know, you got the circle here and you got the line way above it. They're never going to hit each other. Or probably the typical thing is if you draw a circle and a line, it's going to be a secant. It's going to hit it in two places. Okay? Or it could be a tangent line where it just touches the edge of that circle. So the three possibilities for a line in a circle in a plane are that it doesn't hit at all, it hits in one place, or it hits in two places. Impossible for a line in a circle to hit in three or more places. Impossible to happen. The line would have to curve or arc back on itself or something. But it's impossible for a line in a circle to hit in more than two places. Okay, 0, 1, or 2. All right. Okay, so let's look at this kind of complicated diagram here and try to name some of these different things here. And so it says give the best name to the following. So there's a whole list here that we're going to go through. So point C is at the top of the list. Well, if we find point C in the middle of that top big circle, it's the center of that circle. And so it's a center. Okay, the arrowhead got cut off here in the AB, but that's supposed to be line AB. Well, if we look at the line AB cutting through that circle, that's going to end up being a secant because it hits the circle in two places. Okay, now notice here this is a segment CA. Now notice that the segment CA is not even, there isn't a segment CA in this diagram, but that doesn't matter. If there were a segment CA drawn, it would be a radius of that circle. Okay, and again, we can draw a radius anywhere in the circle as long as we draw it from the center out to a point on the circle. That's going to be a radius. Arrowhead knocked off again here, or cut off here. So EA, line EA, if we look at that, line EA is on top of that big circle there. And so it's going to hit the circle in one place only. And so line EA is a tangent line to circle C. You would say line EA is tangent to circle C. Okay, segment DB. Well, again, we're in the big circle on top. Segment BD or DB goes through the center of the circle. The endpoints are on the circle, so because of that, that's a diameter of the circle. It is a chord, but it's a very specific chord that ends up being a diameter, and so we want to give the best name, it says. Okay. Next one, again, arrowhead's cut off here, but it's line HB. Well, line HB is kind of unique, and actually this is a little bit backwards. We probably should have had this slide after the next one, but line HB actually is tangent to the big circle and tangent to the little circle, and notice that the line is outside of both circles. Okay, what I mean by that, and it'd be hard until we compare it maybe on the next slide, but let's say that you moved H to the other side of that small circle, and B kind of went crossed in between the two circles to where it was like a stick between the two circles. That would be a different kind of tangent line. So this one is on the outside of the circles, and so this is called a common external tangent. It's common because it's tangent to both circles. It's external because it doesn't pass through the middle of the circles like that, or between the circles. It stays on the outside of them. And it's tangent because it's tangent to both of them. So it's a common external tangent. In the next slide we'll see, I think it's the next slide, we'll see a common internal tangent to compare. So the best name for that line is a common external tangent. Right? Segment AB. Well, segment AB again is in that big circle on top. It doesn't fit necessarily anything specific, but because it's a segment and the A and the B are on the circle itself, that would be a chord of that circle. Okay. Point A, if you look at point A up there on the top of that circle, it actually serves a couple different purposes, but one of the main things that it hits is that line AE that we had above before, the tangent line. And so because that's the point that's on the circle, that is a point of tangency. So point A is a point of tangency because line AE hits the circle at point A. Therefore, it's a point of tangency. All right, so make sure you understand all those terms because, again, we're going to use them like we're just going to throw those around like everybody knows what we're talking about. So you do need to know those. Okay, so make sure that you can answer all of those questions there. All right. So here we go. So a little bit more about common tangents, and what we mean by common tangents are a tangent to two coplanar circles. So a line that's tangent to two circles in the same plane. Okay. Notice that a tangent can be a line, it could be a ray, or it could be a segment as long as that segment extends beyond the circles. We don't really see segments very often, but sometimes. Okay. And so common tangents hit more than one circle hits two circles. Okay. The difference between an internal and an external is an internal tangent goes between the two circles. Well, the only diagram here that's going to happen is A. That's the only one that we can get a line between the two circles. Okay. And so the question here is, in the white box, tell how many common tangents the circles have and draw them. So as we look at those diagrams, we're going to flip this a little bit. The A diagram there, if you look at the two black circles, there would be 4 common tangents, 2 internal common tangents and 2 external common tangents. So we can draw kind of an X in the middle of the circles and just barely touch each circle at one point. And then we can draw the line on top and the line on the bottom. So there's 4 common tangents there. Okay. With B, when the circles are actually tangent to each other, that's what they're called, they are tangent to each other, then you can draw a line that passes through that one point that they share, and that would be an internal tangent, but then of course the 2 on the outside again. Now when you move the circles to where they pass each other, like in C, then we can't draw an internal tangent anymore because you can't pass a line between the 2 circles because they're beyond each other. So we can only have the 2 common external tangents in that particular case. So you need to understand the difference between those 3 diagrams and the difference between an internal tangent, common tangent, and an external common tangent. Okay. Last slide here. A line is tangent to a circle. This is important here. A line is tangent to a circle if and only if the line is perpendicular to the endpoint of a radius on the circle. Okay. A line is tangent to a circle if and only if the line is perpendicular to the endpoint of a radius on the circle. So let's look at this diagram right here. Question is DE, that segment out there, tangent to circle C? Which, by the way, I failed to mention that in the first slide. When we name a circle, we name it by its center. And so this is circle C because C is the center of that circle. Okay, just one letter, the center of the circle. So back to the question, is DE tangent to circle C? Well, we would have to know that that ends up being a right triangle right there. And so because that CD segment is a radius and it's 3, if we just kind of rotated that around to C, there's no letter there, but between C and E where it hits the circle, that length would be 3 because it's a radius. Plus the 2 on the outside would make CE 5. So that's a 3, 4, 5 triangle right there. Because it's a 3, 4, 5 triangle, it fits Pythagorean's theorem. It's a Pythagorean triple. And so that forces angle D to be a right angle. So yes, it is perpendicular. Therefore, DE is tangent. It must be tangent at that point because it is perpendicular. Okay, so we're going to see diagrams like this over and over and over again. Okay, notice that radius coming out to a tangent. That's always a right angle out there as long as it's a tangent and a radius, or of course a diameter, because a diameter is just 2 radii. Okay. Okay, so how about this one? Tells us that ST is tangent. That means that if ST is tangent, that forces that to be a right angle down there. Angle S is a right angle. Okay, so it's tangent to circle Q. Find the value of R. Well, think about that for a second. R, of course, is the same in both places in that circle because it's a radius. So because it's a right triangle, because angle S is a right angle, that triangle is a right triangle, we need to set up Pythagorean's theorem here. Okay, so we're going to go R squared for the one side, 24 squared for the other side, but look at our hypotenuse. Our hypotenuse, we're going to have to label that to be R plus 18. We're going to have to put those two pieces together to make the whole hypotenuse, right? So if we plug those into Pythagorean's theorem, it's going to be r squared plus 24 squared is equal to r plus 18 as a sum squared. You have to square that whole thing. So we're going to do some algebra here. We've got to FOIL that and expand that and so on. So let's do that. So we get r squared plus 576 on the one side. 24 squared is 576. On this side, we have to write the r plus 18 twice and FOIL it out, multiply it out. So we get r squared plus 36r in the middle plus 18 squared is 324. Now notice the r squareds are going to cancel each other. They're going to drop each other out when you subtract them from both sides. If you move the 324 to the other side, we're going to end up subtracting that from the 576. And so we get 36r is equal to 252. And so if we divide both sides by 36, we're going to get r is equal to 7. So the radius of that circle is 7. All right? So we're using right triangles to be able to solve for the radius of this circle. Okay? Okay, also tangent segments from a common external point are congruent. So if we look at a diagram like this, so we have a point A outside the circle, and B and D, it may not look like it very well in this diagram, but anyway, B and D are actually points of tangency. So AB, it's telling us that AB is a tangent line or segment, and AD is a tangent segment. Okay? So if they come from the same point A out there, they must be congruent to each other. They have to be. No matter where you move that point A, it's going to make those two segments congruent to each other always. That always happens. So we need to set those two equal to each other. So 3x squared plus 4x minus 4 is equal to 4x plus 1. So a little algebra here again. Okay? And so the 4x, if you subtract 4x from both sides, notice it's the same on both sides, it's going to drop out. And then if we move the 1 to the other side, add 1 to both sides, we're going to get 3x squared minus 3 is equal to 0. Okay? Now, you got to remember this from algebra, how to factor this. There's a 3 in common. So we're going to pull that 3 out in front and have an x squared minus 1 left over. Okay? And then we can divide both sides by 3, and so really the 3 just goes away. 3 can't be 0, and so 3 just goes away. The 0 has to come from the x squared minus 1. So we factor that, and remember your difference of two squares, so it factors down to x minus 1 and x plus 1 being multiplied. Okay? So one of those has to be 0 in order for the whole thing to multiply to 0. So if we set the x minus 1 equal to 0, we'd take the 1 to the other side, or add 1 to both sides, and it becomes x equals 1. If we have the x plus 1 equals 0, we would take the 1 to the other side, it would become negative, or subtract it from both sides, it would become a negative 1. But look at our diagram. The 4x minus 1, if x were negative 1, you'd have 4 times negative 1 is negative 4, minus 1 is negative 5. Can we have a negative 5 for that length of that AB segment? No. What would that mean? It falls inside of itself or something? We can't have a negative segment length. So that can't be an answer. We can't have negative 1 as an answer to this. And so x equals 1 is the solution to this equation. Okay? So some review of some algebra there. You got to remember your algebra and foiling and factoring and so on there to be able to solve some of these. Okay? So we're just using the rules of these segments and how they work, how they relate to each other, and integrating some algebra there to be able to solve these things. So, all right? So that is the first section of Chapter 10, starting to talk about circles. So make sure you get all these definitions down and all these theorems down because we're going to use them the rest of the chapter now. So, okay? Oh, Mr. Bedell is back. We'll see you guys.